The shape of a molecule is very important in dictating a lot of its properties. This in part can explain something like why water, H2O, is a liquid at room temperature, while carbon dioxide, CO2, is a gas at room temperature. So far, we have seen the representation of molecules in a very flat, two-dimensional structure. But in reality, molecules exist in three dimensions. So a Lewis structure, although it was very convenient and useful for us, fails to depict the molecule fully. For example, in this Lewis structure of methane, or CH4, it is depicted as a very flat molecule with a carbon in the center and hydrogens equally spaced out in 90 degrees angle. But in reality, the molecule of methane looks like this, with a central carbon atom with hydrogens spiking out from the center. The hydrogens are equally spaced out with about 109 degrees of distance apart, represented neatly in this 3D ball and stick model. Now, it's not as convenient to always draw things in 3D like this with a ball and stick model. So another representation or notation that we have come up with is something called a wedge dash notation. So in a wedge dash notation, everything that is a straight line, like this bond and this bond, that means they are in the plane. Now, what does it mean to be in the plane? When I say something is in the plane, imagine that it is flat. As if you were drawing on a piece of paper, that line would be a part of that piece of paper. Whereas something that is wedged means it's coming out of the paper towards you. Whereas if it's a dash, it's also out of the paper but going away from you. Now, the idea to help us predict the shape of a molecule is called VSEPR theory. It stands for valence shell electron pair repulsion theory. And the acronym for that theory is VSEPR. Now, this is a model that tries to help us predict reality. It works most of the time, and as long as you apply it in this class, you will always get it right. Again, this is a model that helps us predict the shape of the molecule based on the number of electron pairs surrounding the central atom. And the basic principle of this idea is that electron groups like to be as farthest away from each other as possible. Remember that electrons are negatively charged. They are similarly charged to each other, so they want to be as far away from each other as possible. Another key component to understanding this idea is knowing what an electron group is. So what is considered an electron group? A lone pair is considered an electron group, and any bond is considered an electron group. Whether that bond is a single bond, a double bond, or a triple bond, that is one electron group. So as you can see, in order to use VSEPR, you must draw the Lewis structure correctly. When you draw the correct Lewis structure, you can see how many bonds are being connected to the center atom, and you can also see if the center atom has any lone pairs in it. I want to emphasize that this theory only cares about the electron groups that is surrounding the center atom. So with the many ways that atoms can connect with each other in a covalent bond, it will result in various shapes. The first type of shape I want to talk about is when your center atom has two electron groups and is connected to two atoms. To illustrate this point, our molecule of interest would be carbon dioxide, CO2. From the previous lecture, we recall that as carbon dioxide, the Lewis structure looks like this, with a carbon in the center flanked on both sides by two oxygens, and the carbon has a double bond to each of those oxygens. So from this Lewis structure, we can determine how many electron groups is connected to the carbon. How many would you say? Counting electron groups for this carbon, there is one double bond with this oxygen and another double bond with the other oxygen. Two double bonds counts for only two electron groups. Now, if you have two electron groups connected to this center atom, how do you think they would be oriented to each other to be far away as each other as possible? You can close your eyes and extend your arms, right? Imagine your fists are the electron groups. Now move them around your two arms. In what position do you notice that they are farthest away from each other as possible? Now hopefully you have come to the conclusion that if you hold your arms as straight as possible, almost like in a line fashion, they are as far away from each other as possible. And in that instance, they are 180 degrees apart. So from VSEPR theory, in order to minimize repulsion, when you have two electron groups, you will be 180 degrees from each other. This electron group arrangement, because it forms a line, is called linear. The molecular shape is also linear. Now, what's the difference between the electron group and the molecular shape? Now, the electron arrangement is basically the geometry formed from your electron groups, while the molecular shape only counts the shape that is formed from your atoms. In this case, they are both the same because you have 2 electron groups and 2 atoms. We'll see a difference as we move along. So here I have for you represented in 3D this molecule of carbon dioxide. It is a linear molecule with the oxygens farthest away from each other as possible. Again, linear because you can see if you connect the atoms, they form a line. So there you have it. That's our first shape. It's a linear shape when you have 2 electron groups and you have 2 atoms bonded to your central atom. Next, let's talk about what happens when you add another electron group. When you have 3 electron groups, there are 2 options where you can have 3 atoms or 2 atoms. Let's first talk about when you have 3 atoms connected only. Our example here is H2CO. And if you properly draw the Lewis structure, it should look like this with the carbon in the center connected to 2 hydrogens and a double bond to the oxygen. So in terms of electron groups, this carbon would have 3 electron groups. Again, counting electron groups, you would say 1 single bond, 1 double bond, 1 single bond. So you will have 3 electron groups. Now think about this. If you have 3 electron groups, how would you arrange them to be as farthest away from each other? Imagine a circle, dividing that circle into 3 parts. What would be the angle of those 3 parts? Right? It would be exactly 120 degrees apart. So this electron group is 120 degrees away from this electron group, and this electron group is 120 degrees away from this electron group. This electron group is 120 degrees away from this electron group. Now, again, if you think about that, 120 times 3 would be 360. That's a total angle in a circle. So when you have this kind of electron arrangement, the name for it is trigonoplanar. Trigonal because it's 3, and planar because this is a flat geometry. Imagine if you were karate chopping this molecule. Is there a way when you karate chop it, you can chop all 4 atoms at the same time? If you say yes to that, then it is a flat molecule. It is called planar. And the molecular shape is still trigonoplanar. To help us see again the shape of this molecule, I have here the 3D representation of it rotating. Let's take a look at it, and try to see when you can karate chop this, where 4 of the atoms can be touched by your hand at one time. Ready? Should be now or now. You see that? Whenever you karate chop it at this moment, that you can chop all 4 atoms at the same time. When you can do that, that's something called planar. And if something is planar, that's just a fancy term for being flat. Alright, so now we have covered 2 shapes. First linear, now trigonoplanar. And trigonoplanar is when you have 3 electron groups and 3 atoms connected to it. Now there's a second shape when you have 3 electron groups. You can have 3 electron groups, but only 2 atoms connected to it, and that gives you a different shape. Let's take a look at that example. SO2 will be our prime example in this case. And drawing the Lewis structure for SO2, I would see that sulfur is singly bonded to one oxygen and doubly bonded to another oxygen with a lone pair also. So from this Lewis structure, how many electron groups does it have? Right? We said this was a 3 electron group, so let's count it. A single bond, a double bond, and a lone pair. So 1, 2, 3 electron groups. And so when you have 3 electron groups, how are they oriented from one another? Right? They would be 120 degrees from each other. This electron group is 120 degrees from this electron group, is 120 degrees from this electron group, and 120 degrees from this electron group. Do you remember what this electron group would be called? Right, it would still be called trigonoplanar, again, because the 3 electron groups are all in one plane. Now here comes the difference between this molecule and the previous molecule that we just did. When we talk about the shape of a molecule, we just care about the atoms in that molecule and not the lone pairs. So if you were to ignore that lone pair on top of sulfur, how would you describe this shape? It's basically 3 atoms, but it's not in a straight line. It's rather bent. So the molecular shape of this molecule is bent. Again, its electron arrangement is still trigonoplanar, but the shape of the molecule overall is a bent shape. And here's what it looks like rotating in 3D. You can see the red balls there are the oxygens, and this yellow is the sulfur. And it is in a bent shape. It's not a straight molecule, it's bent. And in this structure, you do not see the electrons being depicted. We just finished the shapes you can get when you have 3 electron groups. You can either be trigonoplanar or bent. If you have 3 electron groups and you're connected to 3 atoms, the shape of your molecule is trigonoplanar. But if you have 3 electron groups but only 2 of them is atoms, then your molecule shape is bent. Let's move on to the next group of shapes. We will now talk about when you have 4 electron groups around the central atom. In the first case, we will have it when we have 4 atoms also connected to it. Our prime example, again, is methane, the molecule I showed you in the beginning of the lecture. The Lewis structure for methane shows that there's a central carbon atom with 4 hydrogens connected to it. And from this, so how would you count the number of electron groups? Right? You would say this is 1, 2, 3, 4. 4 electron groups around carbon. There is a shape that allows for 4 corners to be separated equal distance from each other, and that shape is called a tetrahedron. A tetrahedron is a shape that has 4 identical faces. And it turns out when you are in this shape, the angle between this hydrogen, carbon, hydrogen, this angle right here is 109 degrees. That's as far as each other as you can get. Whereas opposed to just a Lewis structure, you will be tricked by thinking that the farthest you can get from it, if it's a flat shape like this, is only what? 90 degrees, right? This hydrogen, carbon, hydrogen, this angle here gives you only 90 degrees. Whereas this one maximizes it to 109 degrees if you have 4 groups that want to be far as away from each other as possible. So therefore, that electron group is called tetrahedral. And for methane, the shape of methane is still tetrahedral. So here's what tetrahedral shapes look like in 3-dimensional. All right, are you ready for our first checkpoint? Can you draw the Lewis structure of NH3 and predict its electron group arrangement? Hopefully you were able to draw the Lewis structure for NH3, and it should look something like this. And from this, how many electron groups does NH3 have? It has 1, 2, 3 single bonds, and 1 lone pair. So that gives it 4 electron groups. If something has 4 electron groups, what is the arrangement of its electron groups? Okay, so far we've learned about 3 electron groups already. You have 2, 3, or 4. When it's 2, it's linear. When it's 3, it's trigonoplanar. And when it's 4, is tetrahedral. Very good. So that brings us to our next shape. We still are going to deal with tetrahedral for electron groups, but instead of having 4 atoms connected to the central atom, let's see what happens when you only have 3 atoms connected. The previous checkpoint question was to prime us for this example of ammonia, NH3. Again, we drew the correct Lewis structure for ammonia. We have already discussed that there will be 4 electron groups, 3 of them coming from the bonds with hydrogen and 1 from that lone pair. Again, to minimize the repulsion from these 4 electron groups, they will take the shape of the tetrahedron. So the electron arrangement again is tetrahedral. But again, when we talk about the shape of the molecule, we don't consider the lone pairs. So if we have this as the electron group arrangement and ignore the lone pair, we have a molecule that looks like this. From the shapes that we've seen already, there is a shape that is connected to 3 atoms. Remember that? That was the trigonoplanar. But is this molecule planar? Is there a way where you can do a karate chop on this molecule and hit all 4 atoms at the same time? No, right? So therefore, this is not planar. What it looks like is a pyramid. If you consider these 3 white balls as the base of that pyramid, the blue ball will be the top of that pyramid. And so, because of that, the molecular shape is called trigonopyramidal. Again, trigonal because it is connected to 3 atoms, and pyramidal because it's not planar, but it's actually in the shape of a pyramid. This is the 3D rotation of NH3 ammonia. Try to see why this is trigonopyramidal from this image. So again, when it comes to 3D shapes, it gets a little bit complicated and hard to draw. So we like to use the wedge dash notation, where a flat line represents something that's in the plane. A wedge here means the hydrogen is coming at me, and a dash means the hydrogen is going away from me. Alright, so we're almost there. We just finished the shape where you have 4 electron groups but only 3 atoms connected to it, and that was called trigonopyramidal. The last shape we're going to learn today is going down the list, what happens when you have 4 electron groups but 2 atoms. Our poster child for this is actually water, H2O. When you draw the Lewis structure of water, it should look like this. How many electron groups does water have? Again, hopefully you should say 4. It has 2 bonds, that's 2 electron groups, and it has 2 pairs of lone pairs, so that's another 2, so that makes it 4 electron groups. Again, if it's 4 electron groups, what is the arrangement of the electron called? Tetrahedral. Very good. However, when we take a look at the shape of the molecule, can you still call it tetrahedral? You cannot, right? Because those 2 pairs of electrons will be invisible when we talk about the shape of the molecule. Now, what would you call the shape of that molecule then? It's similar to what shape we've seen before. Wouldn't you call that a bent shape? So this molecule is planar. You actually don't need this kind of notation to draw it. You can draw with just regular flat lines. Alright, so there we have it. All the shapes, you need to know the electron groups, their names, and what happens when they have different numbers of atoms connected. And from that, you should know the shape of the molecule. You should also know the bond angles associated with each electron group family. Again, you can memorize this, or you can try to use reason to help you remember all of these details. So let's have a checkpoint. What is the molecular shape of PF3? After drawing the correct Lewis structure, you should see that phosphorus is a central atom with 3 bonds, each connecting to a fluorine, and then a lone pair also. So therefore, it is 4 electron groups. However, it is connected to 3 atoms only, so the shape of this molecule would be trigonopyramidal.